Physics Notes, Unit 21, Part B, talking about circuits and Kirchhoff's laws. But before we do Kirchhoff's laws, we'll talk a little bit about real batteries and terminal voltage. So in this diagram down here at the bottom, or in the middle, these two red lines represent a battery. This diagram is right out of our book in Unit 21. But sometimes the fancy word for battery voltage is called EMF, electromotive force, basically the pushing force that pushes the current around. It's really an energy source, converting chemical energy into basically kinetic energy of the moving particles, or electrical energy. But voltage, this battery right here, for example, is rated at 18 volts. There's a red dot here, 0 volts, and a red dot here, 18 volts. So on the positive side of the battery, move this out of the way, that battery is going to give 18 joules of energy per coulomb of charge it pushes through because of the chemical reactions in that battery. So if you were to measure that battery when it's not in use, it'll measure as 18 volts. That's its EMF. That's what they call the battery voltage. And we might say it's an ideal battery. So we talk about ideal batteries. Ideally, that battery will stay at 18 volts always. And it has no internal resistance if it's an ideal battery. But in real life, you have real batteries. So this is depicting a real battery which has internal resistance. The internal resistance of this battery is usually a small resistor that's right next to the battery. In this case, it's 0.5 ohms. 0.5 ohms is the internal resistance of this battery. Okay, so what happens because of the flow of the current, which I'll explain more in just a little bit, this battery actually, when it's put in a circuit, it's supposed to be 18 volts, but when it's actually used, it only delivers 17 volts of energy, or joules per coulomb, to the external part of the battery, because some of the energy gets used up and dissipated to heat inside the battery because of this internal resistance. Resistors cause heat and energy loss to heat. So, or for example, if we applied Ohm's law to this resistor right here, it tells, all the numbers are on this diagram. This blue arrow represents the current flow in this loop. The current flow in this loop, it's a single loop, it's 2 amps everywhere. All 4 elements, the actual battery, the internal resistance, and the other 2 batteries, two resistors. These 2 resistors, which could be light bulbs, are called the load, L-O-A-D. It's the external part of the circuit, external to the battery. If you were to hook up wires to the battery, you'd be hooking up a wire right here at the 0 negative terminal, and the positive 17 volt positive terminal when it's in action. Before you turn it on, it'll say, oh, it's going to be 18 volts, 18 volts. No, but when you use it, there's energy lost inside, like I've said now. That's what they call the voltage drop due to the internal resistance. But bottom line, the terminal voltage then is 17 volts here. And you could go around this circuit, and if you look at this resistor right here, there's 2 amps of current flowing through it. Using Ohm's law, V equals IR. I is 2, R is 6. 2 times 6 is 12 volts. It's a 12 volt, what we call potential drop. All right? It's basically that resistor uses up or converts 12 joules of electrical energy per coulomb into basically heat energy or light energy if it's a light bulb. And you can also see that by the potential going in. 17 volts is the potential. The outgoing potential is 5. The potential difference, the potential drop, is 17 to 5 is 12 volts, 12 joules per coulomb. And then once you get over here to this last resistor, it's a 5 volt drop. So it's a 5 volt potential difference. The other way, you can see that in the 2 numbers here that are labeled. Or if you know the current is 2 amps using Ohm's law, V, potential difference, equals I times R. I is 2, R is 2.5. 2 times 2.5 is 5 volts. It matches up. That's a 5 volt potential difference drop for that resistor. Now there's a diagram here that shows this with these line segments. Let me see if I can get down. Oops. Okay. So this diagram right here is kind of showing the same thing. What it's showing you here with this yellow graph, to me they look like walls, but like going up. Like, for example, this is 0 means 0 volts potential difference, or potential. Okay. When you go from one potential to another, that's the potential difference. So the battery raises up the energy. So this is high energy up here. So this point up here represents high energy. 18 joules per coulomb. Because of the battery voltage, what's called the EMF, and sometimes they just use this fancy E instead of saying EMF. The book likes to use EMF. I'll use EMF. but it means voltage. 18 volts here. And what happens is there's a small drop right here from that point to that point, a 1 volt potential drop because of the internal loss to the internal resistance. Then everything from here along this graph or line or wall is all the same height until you get here. Then you drop down in energy. It's kind of like a roller coaster in a sense. So they give you energy to raise you up, give you energy, and then you roll around, and you drop down, you lose some energy, you lose 12 joules of energy, 12 joules of energy per coulomb of charge. That goes down, that potential drop. Then you're level again until you get to that last resistor, which is a smaller drop, a 5 volt drop, and you get back to your 0 spot. So that's a pictorial, or a picture of one way to think about potential drop around a circuit with battery, real batteries with internal resistance. So let's show you what this. Oh, I went past the equation. Here's the equation then that coincides with that. All right, the terminal voltage. In this case, this battery in this diagram we just did, the terminal voltage is 17. So in the one we just did, the terminal voltage is 17. That's equal to the EMF, which was 18, minus the 1 volt drop from the internal resistance, which we got by either looking at the diagram. 18 to 17 is a 1 volt drop, or 2 amps times 0.5 is 1 volt. So that's consistent. All right. Let me now go down to the problem. So, switching back to red. It says a certain battery has an EMF of 3 volts. And this, okay. All right, yeah, so this is how I'll do this. Let me do a little better job. Let me draw the diagram. So here's a diagram. You might want to pause and draw this. So these two little circles that I have here are the two connections to the battery. We have a 3 volt battery with an internal resistance of 4.5 ohms. It's usually a small number. Hopefully it's small, otherwise it's going to be energy lost internally to the battery. The battery will heat up. Sometimes it catches on fire like you saw in some of those short circuit animations earlier. But the external load here is total. It says total external load is 63.5. Oh, I'm sorry, 65.3. I wrote that backwards. I got to fix that. 65.3 ohms. It says, what is the terminal voltage? Well, the actual EMF of the battery is 3.0, but the terminal voltage will be a little bit less than that. Really, all you have to do is apply Ohm's law, V equals IR, in the simple case here. Now, the V in the circuit is 3 volts, 3.00, equals I. But what you have to plug in here is the total circuit resistance, which is 69.8. 69.8, because that's the total resistance if you were to combine everything, because those are in series. The 4.5 is in series with the 65.3. So that's the total resistance encountered in a single loop circuit like this. If you were a single charge, or a whole bunch of charges, but if you just think about a single charge, it's a single loop, that's the total resistance in series, you add them up. So if you do the math here, okay, not too bad, you take 3 divided by 69.5, and that results in 0.043 amps of current flow in this circuit. That's not our answer, but that's the flow of current, and I'll indicate that this arrow represents the flow of current. Once again, the flow of current doesn't start at the battery. It's everywhere all at the time, but when I draw an arrow, I have to start somewhere, and you usually start at the battery to draw the arrow, but that represents the flow of all, like the musical chair concept. And that flow is 0.043 amps everywhere at every point in the circuit at all times once it's activated or closed and working. So what is the terminal voltage? Well, what you want to do basically here is, as I just wrote down in that equation, V terminal, okay, is your EMF. It's your EMF minus I times R. Basically, I times R is the voltage drop for your internal resistor. So our EMF here is 3.00. Our voltage drop for our resistor is going to be the current through that resistor, which is what, 0.043, times its resistance, 4.5 ohms. So the terminal voltage, not the T there means terminal, not total voltage, is going to be 3.00 minus 0.19. That's basically a loss, 3.19 joules per coulomb. So the terminal voltage here is what? 2.81. Oh man, it should be 2.81 volts. That's basically supplied to our external. And in fact, if you go back over here and check, you can check this for the velocity, the potential difference for this resistor, V equals IR. If you check it out, the current there is 0.043. This is just a check, times 65.3. And if you do the math there, that's 2.81 volts. I'm sorry. Yeah, it is. That's 2.81 volts. Check it out. That checks out to be the terminal voltage. Basically, that's the voltage available to the external circuit. And here, the external circuit we're treating as one resistor, so all that voltage, all that energy goes to one resistor, or it could be split up between several resistors. All right, another example on battery terminal voltage. Car battery. This one's being charged, so we'll make some adjustments here. Let me draw this diagram. So this is a basic charging circuit. I mean, the basic idea is you have another external battery, or it could be a wall outlet, which we would draw a little bit differently, but in a basic, simple charging circuit, you would have another battery that has a voltage greater, usually much greater than the battery you're charging. This is what happens when you charge your cell phones and your laptops. When you plug into the outlet and use the transformer that's part of the charging device, it forces current backwards into your battery, through your battery, and it rejuvenates, energizes, puts energy, chemical energy, into the chemicals that are in that battery. So this 12-volt battery, because this is the long side, the positive side, wants to make current go clockwise. But there's a bigger battery down here, and we don't know how much bigger it is right now. We might not be able to figure that out because we don't even know what the internal resistance of the other battery is. We really don't care right now. Let's see if we have to come back to that. But all I know for now is that this other battery is bigger than 12 volts, probably much bigger, because that's a huge current. That is a huge current. Okay. It says, what is the terminal voltage of our battery? Well, our EMF of the battery is 12. And you'll see some interesting things here. Now, here's the thing, and you'll have to trust me on this for now. Well, the formula is, this is the equation I wrote down, so I mean there's EMF minus I times R. So V terminal, okay, equals EMF, which is 12 volts, minus 60 times, well, I know what the current is, 60 times the resistance, 0.050. But here's a little bit of a new twist, which will be, well, it's important right now, and so it will be important in the future as well. When you have, in a sense, current going backwards through a battery, or through a resistor, and I'll talk more about this later. Right now it looks like magic. This turns into a plus. All right? Or technically, the more technical thing here is, this stays as a minus, but the 12 is a negative. The 12 is a negative. The battery becomes negative instead of positive when you force current backwards through the battery. So its EMF is no longer plus 12, it's minus 12. So the terminal voltage here is negative 12 minus 60 times 0.050, which is 3 volts, 3.0 volts. So the terminal voltage here is negative 15, or we would just say it's 15 volts. You can leave the negative in if you want. It's negative 15. Or if you actually measured it with a device, it would show up as negative 15, and the other battery would show up as positive whatever it is. Some number actually still bigger than that, bigger than positive 15. So it's negative right now. That's the terminal voltage. while it's being charged. So when it's being charged, the terminal voltage is going to be greater than its EMF. When it's being used, its terminal voltage will be less than its EMF. Part B, that was A. Part B, at what rate is thermal energy being dissipated in the battery? Well, the thermal energy is dissipated in the resistor. That's where the resistor is what turns electrical energy into heat energy. And they're asking for the power. What that means is what rate, that means the power. That's asking for the power. And in this case, well, power is V times I, P equals I squared R. Those are the, I'm going to use the second equation. P equals I squared R. Those are all in our bag of power equations. That's energy being dissipated or transferred to heat or other forms. But I'm going to do this for the internal resistance, for the 0.05. So I want to find the power of the 0.050 ohm resistor. Well, it's the current, 60 amps, squared times 0.050. So that's the power dissipated to heat. It's all, wow, hang on. All right, hopefully we didn't lose it here. It's all being transferred into heat due to heat in the internal resistance. And if you do the math here, I believe that comes out to be 180 watts. All right, that's 180 joules per second of heat energy being dissipated. All right, so I worked out all of part C. So we want to figure out the rate at which chemical energy, or rate at which electric energy is being converted to chemical energy. So this big battery here is supplying electric energy. It's supplying electric energy. And it's charging this other battery, the 12-volt battery. So that 12-volt battery is gaining chemical energy. It's storing up that energy. It's not being used right now. It's being charged. So it's the chemicals in there are being energized. So the power of that 12-volt battery, the rate at which energy is being put into it, is down here to the left. The power input is the V times I. It's the basic power equation for electrical components. So V is 12, I is 60. So 720 joules per second of energy is being put into that 12-volt battery. The chemicals are getting that much energy per second. We already said in part B that the internal resistance during this time is also giving off, converting some of that energy to heat, 180 joules per second. So the rate of gain minus the rate of loss, that's the net gain in the batteries, the gain for the battery chemicals themselves, 720, minus the loss, because that's also internal to the battery. It's the loss due to its internal resistance. So you subtract that, you get 540 watts of net gain for that 12-volt battery. And the other battery over here is, well, the other battery, this battery here, is supplying 720 watts. Probably more than that, because there's also some loss in its internal resistance. So it's probably supplying, 800 or 900 watts of energy, and it's being gone to loss in this resistor, the 180 loss there, and then the 720 gain in this battery. We don't need to calculate all that. We've done all the calculations we needed to do, so we don't need to know what the voltage of that battery is. All we know is it's more than 12 volts, significantly more than 12 volts. All right, now measuring devices. Measuring devices used in circuits, physical devices, and some of the terminology involved. We have what's called an ammeter. Ammeters measure current. They measure current in amps, AMPS, but it's called an ammeter. When you measure using that meter, typically you have to use that meter in series with the other components because you must make the current flow through it. I'll show you the example in a simulation in a minute. The voltmeter, right? It's used to measure voltage in volts. When you use that meter, it's connected in parallel. The ammeter has to be used while the circuit is active, because otherwise there's no current flow. So the current has to be turned on, closed, for the ammeter to work. The voltmeter can work, well, for a supply, like a battery. You can measure the potential difference for a battery, whether it's being used or not. So a 3-volt battery or a 9-volt battery should say that voltage. In fact, it'll be its EMF when it's not being used. It'll be usually the higher number because there's no loss right now. It's not being used. So you can measure voltage for a source before you actually use it. When you measure then in a circuit, the passive devices like the resistors, you can't measure their voltage unless they're being used, but batteries, you can measure them whether they're being used or not, whether they're in the circuit or not. I'll show you that. An ohm meter, measure of resistance. And once again, well, that you need to do when the circuit is off. The circuit is open. Open means off. You measure that also in parallel. So you have these things called digital multimeters, which I'll show you. Digital means it shows specific numbers, like most digital watches now, specific numbers, as opposed to dials or needles. That's analog. Old school clocks with dials that spin and meters with dials on them, which I'll show you. A galvanometer is an old analog meter. Well, typically they're old. They're old school. We don't use them much anymore. But they're used. They can be used to measure current or voltage. Potentiometer it's usually, in the case that we're going to be using it, it's going to be used as a variable resistor, or it can be used as a voltage splitter, which I'll show you. And then null measurement. It turns out that when you're making measurements of anything, whether you're using a thermometer to measure temperature or these meters to measure current or voltage, the measuring device itself can mess up what you're measuring. It can change the measurement a little bit. Like if you try to take your temperature, if the thermometer is not at the same temperature as you are, or of the glass of water that you're putting it in, or whatever you're measuring the temperature of, the thermometer itself, the measuring device, changes the thing that you're measuring. And we want to keep that to a minimum. And in the best case scenario, have the measuring device not have an effect at all on what you're measuring. So we have these things called null measurements or null measuring devices, which try to make measurements such that they don't really change what you're measuring. I'll show you some examples in a minute. But before I do that, back to that same circuit we had that we solved previously with the FET. So physical measuring devices. This right here is pretty close to what a real physical measuring voltmeter would look like. This current meter, ammeter, is not what it typically looks like. I'm going to put that away for now. See if it goes back in the box. Oops. Yeah, it goes in the box. Okay. So these things are called probes or leads. P-R-O-B-E-S, probes, or leads, L-E-A-D-S. And usually the black one is 0, and the red one is positive. So black one's negative, red one's positive. This one's kind of a generic. Now, let me just show you, though. This is moving in slow motion, but I think I can take a measurement here. Here's how this is supposed to work. If I take this probe, if I want to measure the voltage of this light bulb, I got to touch in parallel. In other words, I got to touch the bottom where the two wires are connected. I have to touch the bottom. Oh, please work. And the side of that bulb. Okay. So if I want to measure the voltage of that bulb, I got to touch right. Come on up there. All right. Whoopsie. Okay. It's negative 3 volts. Typically, and if you hook it up the other way, you put the red on the bottom, black on the side, it'll get positive 3 volts. But bulbs are typically negative voltage. That's negative 3 volts. Negative 3 volts. So that would be consistent with how we want to run these. If I go up here to the top, oops, everything's moving slow. Come on. All right, so let me go there and go to the bottom of that bulb. So this one shouldn't be 3. Okay, it's, what is it? All right, it's 6.74. It's a different voltage, and it should be negative. I should put if I switch them around, this time I put the red on the bottom. In other words, the spot where the current is going in is at the bottom, and then when the current's coming out at the top, then it would give me that negative number. Let me see if I can do that. These are moving real slow. Shoot. If I touch them together, I'm going to get 0. So now I'm going to put the red one at the bottom. So it looks like they're going to be crossed over each other. It should say negative 6.74. So that's putting things in parallel. Let me move these around here. So for example, let's measure this bulb. I'm going to show you that this bulb here is going to have the same voltage or potential drop. Let's see what it is. Negative 9.74. But it's in parallel with this other one. Notice that the first two in series did not have the same voltage. They have the same current. We measured that earlier. It was 0.7, I believe. But this one, that was negative 9.74, whatever it was. Okay, so this bulb here should have the same potential drop. And we're ignoring the wires. I think it's set up that the wires are 0 resistance. Yep, negative 9.74. So I'm measuring in parallel. I'm measuring on both sides of the objects. That's called measuring in parallel. And for voltage, what that really means is you're not taking anything apart. You're just touching your probes, your leads, to the two sides of the item, the incoming and the outgoing location of the wires that are connected. This one's going to be different now because it's not in parallel. It should have a fairly high voltage. Let's see what it comes out to be. Yeah, 30.26. It's got a lot of current, and once again, if I put the red one on the bottom, it'll give me a negative. Put the red one where the incoming current is, it should give me a negative. Okay, so that's 30.6. All right, now if I go to the battery should be, we said it was set for 40. So this is painstakingly slow, but it's not very fast. No, I guess that's the definition of slow. So for the battery, all right, once again, let me put the black one at the negative side and the red one at the positive side. So that's 40 volts. If you hook it up backwards, it'll just give you the negative answer. So that's the energy supplied. So that's how you hook up a voltmeter in parallel. Just touch the two sides. It's in parallel. It kind of gives you a new pathway, and you'll see that in some of the diagrams. But I'll put that back away. See if it goes away, please. Yeah, there we go. But, let me bring it back out. Sorry. Now, usually this meter here, these digital multimeters, could measure current as well as resistance and voltage. So I just did voltage. If you were to use this as an ammeter, there usually is a dial on here that lets you switch it to a bunch of different settings. First of all, I'll have 3 or 4 settings for voltage, for low voltage, mid voltage, high voltages. Then I'll have 3 or 4 settings for current. But to measure current with a real meter, what you do is, I'm going to click on this, and what happens is if you have to open a circuit, and the circuit stops. Now everything should turn off here. It didn't. All these light bulbs should be off right now. There's no current flowing. I'm not sure why it's still flowing. There's an open. Those are still on because there's still pathways over there. There's still a pathway over there. The current only stopped in this branch. So there's no current flow there, but the other ones are still pathways to the battery. So that is correct. Those are still on. All right, so if I bring this over here, so the way you would use this as an ammeter, it's not going to work right now because it's not set up to be an ammeter, but this is how you would do it as an ammeter. You have to put it in series. You have to put it as like another one, like if I'm putting a bulb right there. So I'm not going to get I'm going to get a reading for voltage right now because it's measuring voltage, not current. But you would set this to current, and it would give me a current reading. So that's how you have to get meters, have to use meters for measuring voltage and current. For current, you have to put the meter in the circuit as part, like an element, and the current must flow through it, like another light bulb. I'm just showing you how it would have to be hooked up in case it comes up in lab. But for voltage, you leave everything hooked up and you just touch the two sides of the element to get the voltage reading. All right, that's a summary of using. One last thing. So for resistance, before you even hook it up, you would take everything off. You would disconnect that. If I disconnect the battery, then everything will. If I disconnect the battery, everything will turn off. Yeah, so everything turns off when you disconnect the battery. And now, what you want to do is individually take them out of the circuit. You can measure their voltages or resistances. There's other settings on this digital multimeter. You could measure low, medium, and high resistances, but you'd have to take them out one by one, and you'd kind of do it like voltage, where you touch the two sides or the bottom of the side of a light bulb to measure the resistance of that item. So here's a picture of some actual real digital multimeters and some of the devices that are defined on the page previous to this. Digital multimeter, it's digital because it has digits there, 9.64. They're measuring a 9-volt battery. That's a 9-volt battery, and its terminal voltage is 9.64 volts. That's probably its EMF because it's not being used right now, so there's no current flowing. So it's a fresh battery, so it's a little over 9 volts. When it's actually used in a circuit, it's probably going to be more like closer to 9 volts. And you can see there's a dial here. It's pointing at the V right now for voltage, but you can turn it to different voltage settings: high voltage, low voltage, direct current voltage, or alternating current voltage. And there's a bunch of different places to hook in down here at the bottom as well, whether you're measuring current. Usually the black wire is always in a spot called COM, C-O-M-M, which is the ground or the common location that never moves. But the red wire right here on the right is probably in a spot where it says V right now. Voltage or ohms for resistance, you can measure both, and you turn this dial to measure different voltages and resistances. But then you move that red wire over to this spot right here where it says MA for milliamps, low currents, and far to the left is probably for high currents. So you can change the settings to measure different quantities, but voltage you can measure well, you have to measure it in parallel, and you can measure that when a battery by itself before it's even being used. A galvanometer is here's an analog. It's got a needle, and depending on where you hook the wires in, you can make it an ammeter to measure current or a voltmeter to measure voltage. So that's just a picture of that. All right, this is a potentiometer, and there's three locations here to hook up. And once again, it can be used as a variable resistor. If you turn this dial, you can increase the resistance or turn it to the left. It decreases the resistance. This is what's called a Wheatstone bridge configuration. It's got 4 resistors that are hooked up kind of in parallel with this galvanometer between points D and B. We will not be doing the math for a Wheatstone bridge, but just to be familiar with it, it's a null measurement technique to get really accurate measurements for the resistance of a resistor. In this case, this tan colored resistor right here, R sub X. The other resistors are known. R sub 1, R sub 3, R sub 2 is a potentiometer where you can set it to whatever resistance you want. So you're going to know the 3 red resistors. And what they do is you take this potentiometer and you dial it and keep turning it until there's no current through this middle branch. Because if there's current through this middle branch, say the current goes from B to D, the needle might go to the left a little bit. Or if there's current going from D to B, the other way to the right, then the needle might go to the right. So what they do is they adjust this variable resistor, this potentiometer, until there's no current. So you get a null measurement. And that way you get a very, very accurate calculation for this unknown resistor. So it's a null measuring technique. That's all you need to know about that. We won't be doing the math on that one. All right, so up next is Kirchhoff's laws. So that'll be part 3 of the notes. But before we go there, friendly reminder, when you're taking circuit measurements with a voltmeter, you put the voltmeter in parallel. Circuit elements in parallel all have the same voltage. And when you're taking circuit measurements with an ammeter, you have to actually disconnect and put it as part of the circuit in series with the things that you're trying to measure.